Hi Vanguards. Hey, we're going to go through a whole bunch of chemical reactions, and what you're going to probably want to have with you right now is this, which says Demo Labs Balancing and Classifying Reaction Types. You can do that if you want to. You can print out a copy, so Demo Labs. You'll also more than likely want to have your PowerPoint, which is going to look like this. I think this might be slide number 8 on your PowerPoint, and that shows you the different kinds of reactions. And then there's some other slides in there that have a lot of good information too. You also want, of course, a pencil and your periodic table, and the yellow periodic table that has the solubility charts on the back of it. The first chemical reaction we're going to take a look at is this one that you've seen a million times before. It's burning gas. And so the gas that comes through the tube there is called natural gas. And natural gas means it came out of the ground not too long ago, and they haven't purified it terribly well. They could purify it into separate things like just methane, just ethane, just propane. Like propane gas is more pure than this. This is natural gas. It's a mixture of mostly methane gas and propane gas. And so on your worksheet, you can type in the 5 different kinds of chemical reactions, and you can find that information on your PowerPoint. Maybe you know those things already, I don't know. So we'll start right off with reaction number 1, the Bunsen burner flame. So 2 types of hydrocarbons. Hydrocarbons means they're made out of hydrogen and carbon, and those are the things that are burning. Okay, so I think you can see this right there. I'm going to write down the chemical reaction. So this is a combustion reaction. That means you have a fuel. So this is the fuel, F-U-E-L. You don't have to write that down. Fuel. And then combustion always needs oxygen, and that's O2. That means an oxygen double bonded to another oxygen. You don't have to write that down either. But just as O2, I think you know that. So it needs oxygen, and then it reacts to make carbon dioxide, CO2, and water, H2O, which is kind of surprising. And so all combustion reactions work like that. The other reaction is propane, so that's C3. Now if you think about carbon bonded to carbon bonded to carbon, okay, each carbon makes 4 bonds, so you'd have an H and an H and an H, another H, another H, another H, another H, another H. So 1, 2, 3, 4, 5, 6, 7, 8 carbons. So that makes sense. C3H, oh, silly, H8. And it's burning too. This propane is burning. That's burning with oxygen, and it's making CO2 and H2O. It's okay, by the way, if you write the methane or the propane second, write the oxygen first. Or if you flip up the products, the CO2, you write that second, write the water first. It doesn't matter. So I just happen to write them in that order. You're supposed to, I think, so those are the skeleton reactions. And now we want to balance them. So when you balance reactions, you put these numbers here, and or here, and or here, and or there. Let me see if you can see the red. I think so. Okay, so those are where we're going to put coefficients. Those are called coefficients. Make sure you know that. And balancing is something that you guys are pretty good at. I noticed that already. So you got 1 carbon on the left, 1 carbon on the right. That's good. 4 carbons on the left, 2 carbons on the right. So we need a 2 as a coefficient here. So now we have 4 hydrogens, and now let's work with the oxygens. Well, CO2 has 2 oxygens. 2 waters have 2 oxygens, so that's 4. So we need a 2 here. We now have a 1 to 2 to 1 to 2 ratio. Actually, that's a mole to mole to mole to mole ratio. Now we don't write ones, so I'm going to get rid of the 1 there, and I'm going to get rid of the 1 there. So even though we know that that's what that is. The second reaction, let's balance that one right now. All right. So you got 3 carbons on the left, and you need 3 carbons on the right. So I'm going to put a 3 as a coefficient in front of this one. I hope that's visible. 3 right there. Maybe I have a better pen. I'll use this blue pen. So I'm going to put a 3 right there. That looks pretty visible. And so that's great. And we have 8 hydrogens, so we need a 4 in front of this. That's a coefficient in front of the water, and that'll give us 8 hydrogens. Now let's deal with the oxygens. We have, on the right side, we have 3 sets of 2 is 6, 4 sets of 1 is 4, so 6 plus 4 is 10, so we need 5 O2s. We now have a 1 to 5 to 3 to 4 mole to mole to mole to mole ratio, and I don't write ones. All right, so those are all balanced, and so that's the Bunsen burner flame. Yeah. So which of the 5 types of reactions is this? Combination, decomposition, single replacement, double replacement, combustion. You know it's combustion. Number 2, what are the 4 hints that let us know that this is a combustion reaction? 4 hints. Well, hint number 1 is this stuff. It's a type of fuel. Hint number 2, it required oxygen. And I can show that to you like this. If I take my Bunsen burner and I cover up where the oxygen comes in down here, cover it up. Let me turn the light off so you can see. So if I covered where the oxygen comes in, that's not a good flame. It looks kind of nice, but it's not burning efficiently. And now let more oxygen in. There she goes. So that's proving that oxygen is required. Another thing that I forgot to get set up, give me a sec, is a nice cold piece of glass. So here's a watch glass. And so let me turn the light on. If I take the Bunsen burner flame and put it on the watch glass, I don't know if you'll be able to see this very well, but just for a split second, whoosh, burn my hand here, it makes fog on there. So the fog is water that's being given off by this reaction. So that shows us that combustion reactions do make CO2, or I'm sorry, that make water, right? They make water, so I'll put the watch glass away. Proof. Now, the other thing, I don't really have a good way to show you that CO2 is made. If we could collect the carbon dioxide and bubble it through something called lime water, it makes a white precipitate. That would be cool, but that's kind of hard to do. So I do have another way to prove that this is a combustion reaction. Combustion reactions give off light and heat. So there you go. You can see the light. Yay, that's a winner. And if I put my hand there, it's hot. So there's your four hints that let us know that this is a combustion reaction. Are these reactions exothermic or endothermic? Exothermic means give off heat. Endothermic means take in heat. Exothermic reactions feel hot. Endothermic reactions feel cold. So you figure out what this is. The second reaction we're going to do is something with magnesium. I've got a little strand of magnesium ribbon right here. Mg. So it doesn't have a charge. You know that magnesium is found way over on the left side of the periodic table. When it's all by itself and it's bright and shiny like this magnesium is, I don't know if you can see it, it has a charge of 0. I could write a 0 right here if I want to. Let me give you a couple more examples. These forceps are coated with some chromium, Cr. Cr. It's shiny, metallic, has a luster, and it's not bonded to anything else. And so that means it has a charge of 0. It's all by itself. If I were to take a hammer and just look at the iron, Fe, so Fe, that has a charge of 0 as well. Once the hammer rusts, then it's going to get a charge of something or other. Now, because Fe is on the left side of the periodic table, it'll get a plus something for a charge. If the rust is red, which it usually is, there's also black rust, but iron often gets a reddish color. That means it has a charge of plus 3 or 3 plus. Fe plus 3 is the bonded form. So it's bonded to oxygen, O, and that has a negative 2. So crisscross applesauce, Fe2, O3. That's the formula for rust. And in this ionic compound, iron has a charge of plus 3. But when it's just sitting there in a brand new hammer and it's nice and shiny and conducts electricity like metals do, it has a charge of 0. I have a little hank of magnesium ribbon right here. All right. So I'm going to take the magnesium and I'm going to put that magnesium. I'm going to turn off the light, put the magnesium in the flame for just a second, and then don't look at the flame. Oh no! It's super bright. Boy, did I ever have a disaster with a kid one time with this. Oh, it's falling on the table. All right, there's our magnesium. Let me turn the fume hood on for a second. All right, you stop burning. Boy, that sure looked like a combustion reaction, didn't it? But in chemistry, you would not say that that is a combustion reaction. A firefighter would say it is because it does require O2 to do its thing. In chemistry, we don't call it a combustion reaction because there's no carbon source here. There's some of this white powder down there on the tabletop. The white powder is something called magnesium oxide, MgO. And I need to figure out the exact formula for MgO. So Mg is in the second column, which means it has 2 electrons in the outer shell. It throws them away and gets a +2 charge. Oxygen's in the sixth column. It gains 2 electrons, and so it gets a -2 charge. And I could crisscross applesauce, get a 2 and a 2, which is the same as 1 to 1. And we don't write 1s. You just use my logic and say it's MgO. All right, it's time to balance this. Grab I'm going to try an orange pen this time, see if that works any better. All right, in chemical reaction, matter is neither created nor destroyed. So here's my arrow. Beforehand, the reactants, I had 1 Mg. Afterwards, I had 1 Mg. That's great. I had 2 oxygens when I started, 2 oxygen atoms, double bonded to one another. So 2 here, so I need 2 here, so I'll put a coefficient of 2 right there. 2 in front of the MgO. Let me see if I can move that. So there's a 2 right here, 2, that's the coefficient. Oh no, I just wrecked the Mg, so I have 2 Mg's on the right, I need 2 on the left, so I'll put a 2 in front of that. I now have a 2 to 1 to 2 mole to mole to mole ratio. Write the skeleton reaction, we did that already. Mg plus O2 yields MgO. Then we balanced it by putting a 2 and a 1 and a 2 in there as coefficients. Wait a minute, Jergens, we don't write 1s. Which of the 5 types of reactions is this? Combination, ooh, this is tough. Don't say combustion because there's no carbon source and you do not make CO2 and H2O, so it's something else. Well, we started off with 2 little things and we combined them together to make one big compound. So which of those reactions is that? Answer is, it's a combination reaction, letter A, also known as synthesis, also known as composition. Why is this reaction not classified as a combustion reaction? After all, it does make heat and flame, so it is exothermic. Well, it doesn't have what over on this side? It does not have, I'll give you a hint, its atomic number is 6 on this side. And over on this side, it doesn't make some of the stuff that falls from the sky, and it doesn't make some of the stuff that you breathe out. So that'd be CO2 and H2O. Do you think that the reactants or products weigh more? What do you think of that? In a chemical reaction, matter is not created or destroyed. That is a trick question. However many grams of magnesium and oxygen you start with, you get the same number of grams of magnesium oxide. And even though oxygen is hard to weigh, it does have weight, it does have mass. You can feel it pushing against you when you go out on a windy day. Do you think that the magnesium metal or magnesium oxide has a higher molar mass? So the molar mass of magnesium, you do not use this coefficient to calculate the molar mass. We're going to be doing that later. So you need to look on the periodic table, and magnesium has 2 numbers. It has a 12 and a 24, I think it's 24.3 maybe. So the molar mass is 24, and it's just magnesium. Do not use the coefficient to calculate molar mass. But when you come over here, MgO. Again, we're not going to use the coefficient to calculate this, but Mg weighs 24 or 24.3. Oxygen has 2 numbers in the periodic table, an 8 and a 16. And 16 is the mass, so 24 plus 16, I think that's 40. Is it not? And you need units for that too. So it's 40 grams per mole. That is the molar mass. Reaction 3, potassium chlorate and sugar, we'll do that next.